So it's probably best for you to think of this lesson as being just the formal teaching of putting it all together, as well as just a time for practice. We're going to be practicing together, and on your own, you're going to be practicing as well a variety of different graphs. This is on page 36 of your unit handout. We've already done problems where I've expected us to sketch all of the details of the functions. And when sketching the graph of any function in this course, you're expected to be able to include in your analysis any symmetry. We've discussed the fact that the symmetry is an important aspect, but it's maybe more important just because it shortens some calculations. For example, in the question that Lauren and I were just talking about, I calculated f of negative root 3, and then I said I'm not going to bother calculating f of positive root 3 because I know the function is even. In addition, if you know that the function is even or odd, and you get a table for the first derivative or the second derivative which doesn't reflect that, no pun intended, there's no symmetry to the table. In other words, you've got a critical number for the derivative of 5, but you don't have a critical number at negative 5, then that means you've done something wrong. So it's kind of an internal check. Obviously, you should always be looking at determining all of the intercepts. In the end, when we start to put together the increasing and decreasing and concave up and concave down and all that other stuff, it helps to have some guideposts along the road that you know you have to connect. And those are the intercepts. As well, you should look at the equations of all asymptotes. As long as the function is rational, which means that expressed in simplest form, it's a polynomial or a variable over another polynomial or a variable, then you have to consider asymptotes. If there are no fractions involved that are variable, then there are no asymptotes. You have to determine the coordinates of all maxima and minima, and in order for you to do that, you have to find the first derivative. You need to complete a first derivative chart. So in the end, you look at the chart to determine the coordinates of max and min regions. I shouldn't say regions, max and min points. But along the way in that chart, you also identify where the function is increasing and where the function is decreasing. And that's just as important as knowing the coordinates of the points that are max or min values. Because, I'm just going to turn my phone off, because it allows you to know when you're sketching it whether you should be drawing uphill or downhill. And finally, of course, you need to determine intervals of concavity. And it's the same kind of argument. Whatever you do to the first derivative to find extreme points, you do to the second derivative to find inflection points. With the first derivative chart along the way, you happen to identify intervals of increase and decrease. And with the second derivative along the way, you happen to identify intervals of positive concavity and intervals of negative concavity. And that's everything in a nutshell. You have to be able to do all of that. Now, when you look at this handout, I believe I've got 7 examples up there. And if you understand what's involved here, I hope you understand we're not going to do all 7 examples. We're going to start off by doing one example together. And whatever example we decide to do, that may be the only example we do. Because along the way, you're going to have questions about the problems I'm going to assign you from your textbook, and we may end up doing them as well. And remember, based on hopefully what you remember from the past couple of days, this is not a quick process. If I say sketch a complete, detailed snapshot of this function, this could take you 45 minutes. And if you make a mistake somewhere and you get to the end and things aren't making sense, it could take you even longer. It might only take you 20 minutes, depending on your skill set. So we're going to randomly pick one here. I've got a random spinner, and let's just see what happens here. We're going to do number 4. And I don't know that there's enough room on that page to do this. You may want to have extra paper. I can tell you right now that looking at number 4 is not one that's going to take us very long to analyze compared to some other ones. So let's start off with symmetry. Because we're formally putting everything together right now, I'm going to show all my work here for this. Symmetry is discovered or found or excluded by determining what f of negative x is equal to. Well, f of negative x would be found by replacing every x with negative x. I'm just curious, and we have lots of time, we're not in any rush. Take a minute and answer this question in chat. How many of you knew the symmetry just by looking at it initially? A few people. I suspect that those few people who knew what the symmetry was were essentially looking at this in their head, would be my guess. You're looking at the top of this and you're saying, since it's to the 1, if I put negative x in, it's going to flip signs and become negative of what it is. The bottom is raised to the 2, so it's going to not matter if I put a negative x in, it's going to stay the same. But let me simplify this now. We have f of negative x equals negative x over x squared minus 1. So what does that give us? That gives us, whoops, I forgot my x. I wrote the top, which is negative x, as negative 1x, because now I'm going to take that negative 1 and just load it in front and have x over x squared minus 1. And this is the original function. What does that mean? It means f of negative x is equal to negative 1 times f of x, and that is the definition of odd. So it has odd symmetry. I'm going to compile all of my information on a separate sheet here, electronic sheet. So I'm just going to write the word odd here. I don't want to pack too much onto a single page because then it messes with the memory. What else did we want to find? We wanted to determine the you want to determine the intercepts. So the y-intercept is found by replacing x with 0, and you have f of x or y equals 0 over 0 squared minus 1, which is 0. And as is so often the case, not all the time, but as is so often the case, we end up with a y-intercept that's 0, which means the graph passes through the origin. So we've also stumbled upon the x-intercept. So we have a y-intercept at 0. You also have an x-intercept at x equals 0. If you didn't see that because of the y-intercept, then what you do is you focus your attention on the numerator of the rational expression and ask yourself what value of x makes it 0, because that will make the whole thing 0, which means y is 0. So what do we know? We know in terms of intercepts, that the graph passes through the origin. I don't think I need to write the y-intercept as 0 and the x-intercept as 0. Incidentally, 0 for x is the only x-intercept because the only factor in the numerator is x. Let's talk now about asymptotes. We have the function y equals x over x squared minus 1. To determine vertical asymptotes, you always want to look at the denominator. This is for vertical asymptotes. And in order for you to figure out where the denominator is 0, it's useful for you to factor the denominator. We're going to have a vertical asymptote at -1 and at +1. I'm going to add that to my list. I'm not quite done with my discussion on asymptotes. I suspect that many of you would not need to actually look here to determine those asymptotes, because I think many of us, maybe all of us, when we see x squared minus 1, we see x plus 1, x minus 1. The other point I want to make is, since none of those two factors, since this factor, which produces a vertical asymptote, and this factor, which produces a vertical asymptote, since none of those factors appear in the numerator as well, it's not possible to cancel them, which means those non-permissible values are in fact vertical asymptotes. If they canceled, we'd be dealing with holes and we would have to go down another road. In terms of, so this is for the vertical asymptotes. For the horizontal asymptote, and I'm using singular here, I'm not saying asymptotes, I'm saying asymptote, because more often than not there's just one horizontal asymptote. We might encounter a case where there's two. That is found by finding out if the limit as x approaches infinity of the function has a value. And this is where you use that rule. Sooner or later, by the way, this rule is going to fail you. You'll go to use this rule with a function and it won't work. So it's kind of limited. But the rule for rational functions is you identify the highest degree term in all those red terms. We've got x and x squared and 1. The highest degree term is x squared, and you divide everything by x squared. And then you simplify each of those terms individually. So we have the limit as x approaches infinity. Well, x over x squared can be reduced to 1 over x. X squared over x squared becomes 1. 1 over x squared is what it is. And at infinity, I don't know what I'm about to write is something you would write on a university exam, but at infinity, this becomes 0 and this becomes 0. So the limit ends up being equal to 0 over 1 plus 0, which is equal to 0. And we could have used the Math 30 rule, which says since the degree on the top is smaller than the degree on the bottom, I'm looking over here at the original function, then the horizontal asymptote is at 0. So now we've got more information I can pile onto the list here. Horizontal asymptote at y equals 0. Which is that's a lot of information, really. That's going to be helpful. We know that we have 3 asymptotes. We know that the graph passes through the origin. I will tell you right now that the end result is this graph is going to be, in my mind, kind of boring. There's nothing really amazing about looking at the picture. But the only stuff we have left now to do is to identify the derivative. And the second derivative, well, not identify, to determine those two derivatives so that we can do the first derivative chart and the second derivative chart. Okay, so what do we got going on here? We have y equals x over x squared plus 1. The first derivative is going to be found using the quotient rule. So the derivative of the top, which is x, is 1 times the bottom. Is the bottom x squared minus 1? Better be careful here. I think it's x squared minus 1. Yeah. So just in case you didn't catch that, I'll put it in a different color. I put x squared plus 1 by mistake. So go back to the beginning of my explanation here. When I notice that, the derivative of the top is 1 times the bottom, which is x squared minus 1, minus the top, which is x, times the derivative of the bottom, which is 2x, and then over the bottom squared. So our derivative becomes dy dx is equal to, I have x squared minus 2x squared, which is negative x squared, and then I have negative 1. I'm just going to do this off on the side so that you can see it, and also so that I can just double check my work. Something as simple as that is easy to make a mistake. I have negative 1 minus x squared. No, it's fine. And this is over x squared minus 1, quantity squared. Again, this is going to be why this is kind of boring, this function. And we went with what the spinner picked, but that's okay. We get this. So what we end up with for critical values of the derivative are critical values of 1 and negative 1. And those are asymptotes. At x equals 1, there's an asymptote. So the reason why those are critical values of x is, for the derivative, is the function doesn't exist there. And if the function doesn't exist, the derivative is not defined. But the chart that we're going to do is not going to reveal max-mins to us. It's simply going to reveal whether the function is going up or down in the particular intervals. So we're going to construct that table by having negative infinity to negative 1, negative 1 to 1, 1 to infinity. Across the top, we are going to have negative 1, 1 plus x squared, and then x squared minus 1 squared. The product of these, well, there's a quotient involved, but we're going to use those columns to determine what the derivative is, to determine what y is, what y is doing. So negative 1 is negative everywhere. 1 plus x squared is positive everywhere, because whatever x squared is, it will be a positive number, or 0, but if we're going to add it to 1, we're going to get positive. X squared minus 1 quantity squared is also positive. So this is weird. The first derivative is negative in the first interval, negative in the second interval, negative in the third. The function is decreasing everywhere. By the way, even if the function were decreasing then increasing in this example, that wouldn't indicate an extreme value because those critical numbers are asymptotes. There are no points there. So, big deal. What we have done after doing the first derivative and the first derivative table is determined that the function is decreasing everywhere. Okay, let's do the second derivative. I am going to choose, when I differentiate the first derivative to get the second derivative, I'm going to choose to differentiate it in this form, because then I don't have to stop and think about, oh, the derivative of a constant times a function and all that other stuff. I'm just going to differentiate from the form on the right. This is the second derivative, d2y dx squared. The derivative of the top is negative 2x times the bottom, plus the top, minus the top. And I really am resisting the temptation to change all of those to pluses right now. But it's minus the top times the derivative of the bottom, which would be 2 times x squared minus 1 to the 1 times the derivative of what's inside, which is 2x. And it's over x squared minus 1 to the 4. I'm going to pause there. I'm going to mentally check over my work in going from this line to this line. You can do the same, and it'll give you a minute to catch up if you're still writing. And to keep you on your toes, go ahead and type into chat if you feel that that is right and there's no mistake there. Okay, good. It's a good reminder for me too. When I ask that, it takes a little while to get responses, but it's a good reminder to me too that you're still catching up in the thought process and the writing process. So if I need to go slower, please let me know. All right, it's at this point in time I feel confident and safe in doing this. I don't think I'm risking making a mistake here by changing those to positives. I'm simply saying if I factored out a negative out of the negative 1 minus x squared, it would cancel with the negative in front. Now I'm ready to factor. Oh boy, you know what? I am going to rewrite this. Let me rewrite it with those pluses in there, and then I will tell you why I'm going to rewrite it. And I took that 2 times the 2x and wrote it as 4x. I'm rewriting it because I want to factor that negative out of the top. And after telling you that I've changed all those negatives to positive, now I'm going to factor a negative out. That might confuse you. So if I factor out, just want to double check that I didn't miss an exponent or anything there. We're okay. If I factor out of that a negative, I can take out a negative 2, I can take out an x, I can take out an x squared minus 1 to the 1. So out of the first term, out of this term, what is it I have left? I have x squared minus 1. Out of the second term, this is the second term, what do I have left? Well, I took a negative out of the positive, so now I'm back to a negative. I took out an x, that x here is gone. I took a 2 out of this 4, so I have a 2 here. I took this whole thing out, so I'm left with this. and now it's over x squared minus 1 to the 4. Again, I'm going to pause there for a breath and let you double check the work from the top line of your screen to the next line. It might help some of you see what's going on if I do this. Look okay to you? Okay. It's what I've told you before about some of the math in this course. Careful, deliberate, organized, slow, but not too slow work. You're checking all the time, you're calm, you're not getting excited and losing track of what it is going on in your head. If you are and you find yourself in a place where you're trying to get some of this work done and you're getting frustrated and you're making mistake after mistake, which happens to all of us from time to time, then you need to take a break from it, watch a funny cat video, and then get back to the math. Just clear your head. That negative 2x is on the top. I can take the x squared minus 1 to the 1, which is on the top, and reduce it with one of the 4 x squared minus 1's on the bottom to get x squared minus 1 cubed. And what do I have left? Well, again, I don't want to cut any corners. I have x squared minus 1 minus 2 minus 2x squared. So multiply that through, I get negative 2. Multiply this through, I get negative 2x squared. I end up with a negative 2, then I have negative 3 for the constants minus x squared, and it's over x squared minus 1 quantity cubed.
I have a question.
Yeah, I'm just going to look over my work here, but go ahead, Aaron.
What happened to the x beside the 2?
That's what I'm going to go back and check. There should be this. Let me tell you, have I got it back now, Aaron?
Yes.
Okay, I forgot to move that x down. Let me tell you, and not everybody here is going to be able to do what just happened in my head, but I was already starting to build a picture of what this graph looked like. And I knew that it went through the origin, and I knew that it was decreasing everywhere, and I couldn't see how it could go through the origin decreasing everywhere unless it inflected there. So I missed that x. By the way, I can simplify this greatly by multiplying that negative through, or if you like, factoring a negative out of this binomial and canceling it with the negative in front of the 2 to get d2y dx squared equals 2x times 3 plus x squared times x squared minus 1 cubed, giving me critical values of plus or minus 1 and 0. 0 for the x in the numerator, and plus or minus 1 for the denominator. Again, though, everybody, if you have vertical asymptotes at x equals 1 and negative 1, the function is not defined there, which means the first derivative and the second derivative will both be undefined there. So I'm going to need to construct my table using the whole width of my screen because I'm going to have to include for all of my factors 2x, 3 plus x squared. Now, I'm not saying you can't put this entire thing in its own column. You can. You could put the whole derivative as one column, or the whole second derivative. What I'm going to do, though, is put this. I'm going to factor the x squared minus 1 into x plus 1, x minus 1, and recognize that they are both cubed. So the table is quite lengthy. I have a column now for the second derivative, and I have a column for y. My critical numbers were -1, 0, and +1. So I'm going to go from -infinity to -1, from -1 to 0, from 0 to 1, from 1 to infinity. By the way, and I'm just mentioning this because I had a prof years ago in university that did what I'm about to say to you, and I talked to a student a couple years ago and they had a prof that did it as well. What you might be told in post-secondary is, since you know that this function is odd, you only need to do half the table and then flip everything around. Although true, I think that's very bad advice. I've tried doing that and I can't wrap my head around it. I would rather just do all the work. So 2x I'm treating as a single factor is negative, negative, positive, positive. It switches when it passes 0 because 0 is the value of x that makes 2x nothing. 3 plus x squared is a positive quantity regardless of what x is, because when you square x you will get a positive number. Added to 3 you will get positive. X plus 1 is negative before -1 and positive after -1. And since this exponent is odd, if x plus 1 is negative, when you cube a negative, you still get a negative. When x plus 1 is positive, cubing a positive gives you a positive. In other words, because that exponent is odd, we treat the whole thing as if the exponent isn't there. X minus 1 is negative, negative. It's negative until after it passes 1, where it becomes positive. And again, since this exponent is odd, raising a negative to an odd exponent keeps its negative. So what does this tell us? This tells us 3 negatives is negative, then it's positive, then it's negative, then it's positive, which means the function is concave down, concave up, concave down, concave up. There's a lot of work that we did here, and the result is going to be a fairly blah graph. Okay, so take a minute, construct a set of axes. I don't know that it's absolutely necessary, but some people do benefit from having this line up here. We can put in our intercepts, of which I'm going to need a little bit of help here, everybody, of which I believe the origin is the only intercept. Good. I know that the line y equals 0 is a horizontal asymptote, and I know that there's a vertical asymptote at 1 and at -1. We did have critical values of x for the first derivative. I need help again. The first derivative had a critical value at -1 and at +1. Yes? Okay. But what we discovered, which was very much a letdown, is that in the first interval, the function was decreasing. And then when we got into the second interval, the function was decreasing. Okay, and then when we got into the third interval, the function was decreasing. You know, I just wanted to say a second ago, that's not very helpful, but you know what? That's extremely helpful. That tells us that whatever we draw has to be decreasing. And there were no max-mins. Correct me if I'm wrong, but for the second derivative, we had critical values at -1, 0. I want to just do something here. 0 and +1. I didn't see if anybody typed anything there. For the second derivative, we had critical values, okay, at -1, 1, and 0. And what we discovered, and I'm going by memory here, so I need your help again, is that in the first interval, it was concave down. And then in the second interval, it was concave up. Then it was concave down. Then it was concave up. I'm pretty sure my memory is right on that. Okay. So, you know, we have overlap of intervals here. This whole region from here to here, the first derivative and the second derivative both have intervals there. And we have to draw something that's asymptotic, that is concave down, and that is decreasing. Well, not much you can do there. It looks like this. Similarly, over here in this region, we have to draw something that is concave up and decreasing. Well, it has to look like this. Incidentally, imagine that you had decreasing and concave down. That would be an impossibility if there are asymptotes. There's no way that you could draw something that is decreasing and concave down. It's impossible. So there's all these, as I call them, internal checks that we do along the way, and we ask ourselves if it makes sense, and it does. Now, what about in the entire middle region? One thing I didn't do, and I really should have, I want to go back to my second derivative chart. Is this an inflection point? I want everybody to think about that. It's going from concave down to concave up. Is it an inflection point? Aiden's saying no with a question mark. I want to wait for a few other people to weigh in. Is this an inflection point? Prince says no definitively. The reason it's not, Aiden, why is it not? Turns out, Aaron, it's not an inflection point.
Is it because there's no points at 1, it's undefined?
Right, the function is undefined there because there is a vertical asymptote. When you, I'll come back to this idea in a second, but what we could call it is an inflection of the function, but it's not happening at a point. The function is inflecting somehow. It's going from concave down to concave up. So there's no inflection point there. There's no inflection point here. This is an inflection point. I think this might be the first time we've encountered this. Just because the table says, oh, it goes from one concavity to the other, doesn't mean it's an inflection point unless the point exists. It's very similar to max-min and the first derivative. If you had a function which was increasing, and then was decreasing, does that necessarily mean there's a maximum? Well, if the point is defined, yes, but if there is no point, no. So what I should have added to our list, if I were to go back to the beginning here in my summary, I have all of this. All the first derivative told us is it's decreasing everywhere. There are no max mins. What the second derivative tells us is there's an inflection point at 0. Why at 0? Well, take a look at your second derivative chart. That inflection point is occurring, that change in concavity is occurring as the function passes through x equals 0. And by the way, to find the y coordinate, you have to put 0 into the function, but we already know the function passes through the origin, so we know the y coordinate. Now, why did I get all off track there? It's because I wanted to discuss what's happening in the middle. And in this region here, it's decreasing and concave up, and in this region, it's decreasing and concave down. There's only one way that can happen. And it's for it to change concave, oh, that's not happy with that. For it to change concavity as it passes through the origin. And then you get a nice graph. And as I said to you, I mean, that's a beautiful looking graph, but there's nothing really weird about it. It's a run-of-the-mill rational expression graph. We're not doing another one. I just want to run this thing again. Oh, number 4. Didn't we just do 4?
Yes, we did.
Okay. Well, sometimes you roll a die and it comes up the same 2 times in a row. Had the question been 7, this would have been an interesting one, actually. Even though it's polynomial, I suspect that because there's no x squared term, it's going to be a little bit weird. So I think that's it for examples. We might do one more example later today, or we might not. We might or might not do one tomorrow. On page 240, there are 12 different graphs. Now, the terminology in your textbook is, it says discuss each graph under the headings, I believe, A through H. Your textbook has categorized all of these things into those 7 or 8 headings. So A might be intercepts and symmetry, and all this stuff is A through H. The bottom line is you want to be able to do everything we've done, come up with a really decent picture of what the graph looks like. And that's what we're working on for the next basically hour and a half here. Clearly you're at home or wherever you are. Hope you're at home, not just sitting someplace in your car. You need to take a break, take a break. You need to give your mind a rest, give your mind a rest. If you have questions, please let me know. And I would definitely recommend starting with question 1, because I think 1 is actually an interesting graph. When you get everything done and you try to piece it together, it's a real brain buster on how it fits together. Try not to cheat. Don't use your graphing calculator. So if you need help, let me know, and I will be there for you.